Okay, hello. This is my video for our Chapter 17 homework assignment, which is dealing with energy and momentum in rigid bodies. So this is problem number 1 here. In this problem we have to use our work and energy concepts to solve the problem. The problem tells us that we have a small flywheel punch that's rotating at 300 RPM. And the first thing the problem wants us to find is the required moment of inertia to keep the speed where it needs to be for the punch to work properly. And so the first thing I did was just take these terms it gave us here, and we know that that is an omega term because it's rotations per minute, RPM. And I converted that into radians per second. And then our final omega here, we know is 0.9 of our initial omega, omega naught. And so just taking this term and multiplying it by 0.9 gives us that term there. And then it tells us also that the work done is 800 foot-pounds. So that is our U term. And so the first thing I did was just write out this equation here where we have the potential energy and kinetic energy before plus our work has to equal potential and kinetic energy after. And in this case we know we can cross out the potential energy on both sides. And so looking at this, we know that this is the equation for kinetic energy, and since the velocity at the center of the wheel would be 0, we can cancel out this term. We know it's all rotational, there's no translational movement in this problem. And then our I term is unknown. That's what the problem wants us to find. And the 10 pi is the omega that was given to us. So that is kinetic energy before. And then the same process can give us the kinetic energy after. We just use our omega for punch after. And then all we have to do is plug the terms that we found there into this equation here, which gives us this. So we have our two kinetic energy terms and our work term. And then all we have to do is solve this for our moment of inertia I. And so I cleared the fraction by multiplying through by 2, and then pulled the I terms to the same side, factored out the I pi squared, and then solved for I to get a final answer of 19.198 pound-feet per second squared. So that's the answer for part A. For part B, we were asked to find how many revolutions must occur between each punch. And we were given that there was a couple of 25 foot-pounds. And so that is our moment here. Our omega naught is the same as problem part A. And basically we want to find our change in theta and then convert that to revolutions. And so what we can use is this equation here where we know that work done is our moment times our change in angle, delta theta. And so to find delta theta, we just have to plug in what we were given. So we were given this moment in the problem, and we were also given our work done. And so plugging all of that in and then converting to revolutions by dividing by 2 pi gives us our answer of 11.459 revolutions. And so that's the answer for part B on this problem. So on problem 2 here, we have this slender rod, and it starts out horizontal, and the weight of this rod is going to make it swing down until it reaches the vertical position. And the first thing the problem wants us to find is the angular velocity, omega, of the rod as it reaches and passes through this vertical position here. And so we're going to use work and energy to solve this problem. And so the first thing I did was just write out our work energy equation that has initial potential and kinetic energy and final and potential energy. and kinetic energy. And then looking at this, there's a lot of terms that will actually cancel out. There's no kinetic energy before because it starts from rest, and there will be no potential energy after because it has reached the bottom of its swing, which can have the bottom height. And so knowing that simplifies, I just wrote down the terms for our potential and kinetic energy that we know. And then for T2 over here, we know that there's the translational portion and the rotational portion. This is our equation here that we know. And so to solve this, the first thing we can do is figure out what I for a rod is. And we know that that is 1/12 ml squared. So we can plug that in for I. And we know that velocity is r omega. And so we can plug that in, giving us this equation, which we can simplify down to make T2 just simply 1/6 ml squared omega squared. And then for the potential energy before, we know that the height will actually be L over 2, this distance from here to here. And that's because if we look at this picture here, once this rod falls down, this distance here that it fell will actually be L over 2. And so using that, we can plug in L over 2 there, and then we look at this equation and it actually simplifies quite a lot. The mass actually cancels, so we don't need that. And then multiplying the 6 over, one of the L's will cancel as we move those over, and then we take the square root to find out that omega equals 3 times g over L, and the square root of that. And so that's the answer for part A. And then part B gives us our weight and our length. And we actually don't need the weight for this part because it canceled out, but we can just plug in our length and our known gravity of 32.2 and solve that to find an omega value of 5.67 radians per second clockwise. And then the next thing the problem wanted us to find was the reaction forces at A here. And so I drew this little diagram here to help me visualize. So once this rod, the slender rod, reaches the vertical position, there's really only two forces. There's A going up and our weight pulling it down. And so writing an equation from what we were doing in the previous chapter, in chapter 16, we can sum the forces in the y direction. And so we have, like I said, A minus our weight, and that has to equal mass times acceleration. And then we know acceleration has to equal r omega squared. Plugging in what we know from the problem, we can simplify that equation to get this term here, and then moving our weight over. Weight is mg, and then adding this, we have 3/2 plus 1 gives us our 5/2 mg up, and so that is the reaction force at A. And then solving this with our given information, we were given our weight of 1.8, which we know is the same as mg, and so all we have to do is multiply our 1.8 by the 5/2 that we figured out, giving us a reaction at A of 4.5 pounds upward. For problem number 3, we have these two rods here that are, the problem tells us they're welded together at this 90-degree L shape, and that this spring here is going to cause this L shape to rotate upward, and it tells us that the maximum angle of rotation of this assembly is 90 degrees. And so I drew that in here, so the dotted line is after, so this will be this will swing up to that position. And the question wants us to find out the magnitude of the angular velocity of the assembly as it passes through the position where rod AB forms a 30-degree angle. And so that's what I kind of drew here to help me visualize it. And so as this swings up, we're interested at the point in time when it reaches a 30-degree angle. And so in order to solve this problem, we want to use our energy equation. And so what I did was I just thought about the potential energy before and after, and the kinetic energy before and after, and then we can plug those into our known equation and try and solve for omega. And so looking at this, the first thing I did was look at this picture here and try and find the final kinetic energy of this shape when it's all the way up to this 90-degree rotation when it's flipped up. And so at that point, there will be no more kinetic energy because it will stop moving, and the potential energy will only be from the rod that is horizontal here. And so we can write this equation for the potential energy at that point. And so that will be one side of our equation. For the other side of our equation, we need to know the potential and kinetic energy at this 30-degree angle, which I just called T30 and V30. And so we know that T30 will have to be 1/2 I omega squared. And we need the I for both of these rods that are welded together. And we can look at the rod. We can use the equation 1/3 ml squared for I, because we can go from the point of the rod here where it rotates. And so that's the equation we need to use, and then we do that for both rod AB and BC, and so the total inertia will be the sum of both of those. And then we can just factor out the 1/3, and it simplifies to this. As far as the potential energy at this 30-degree angle, we have to take that angle into account, and so we have our weight for both rods. So once again, we have to find the potential energy of each of these rods and then add them together. And so we have the weight of the first rod divided by, or multiplied by L/2, which is the center point of the rod, times the angle that this makes. And so then for rod AB, it will be sine of 30, and for rod BC, it will be the cosine of 30. And so that would be our potential energy term at the 30-degree angle. And then all we have to do is take those four terms and plug them into our energy equation. And so, like we stated up here, the final kinetic energy will be 0, and so we can cross that out. And then we can plug in these three terms that we found up above here. And so that gives us this equation here. And then we want to solve for omega, because that is what the question was asking us for. And so rearranging this to get omega by itself gives us this equation. And then we can plug in what we know from the problem and cancel out some things. That gives us this equation here. And then from there, we can plug in G/L and then take the square root to get that our final omega is 7.09 radians per second. And so that is the final answer for question number 3. Okay, hello. So this is problem number 4 in this homework set for chapter number 17. And on this problem, we're switching over from the previous problems where we're using the concept of work and energy, and we're now using momentum and impulse concepts to solve the problems. And so in problem number 4 here, we're given this tire, and we're tightening on a lug nut here using this wrench. And looking at the diagram here, we can see that we're twisting both ends of this wrench in equal and opposite directions, which means that we're going to be creating a moment around this lug nut here, or this bolt. And so the problem, the question wants us to find is the angular velocity of this wheel that is caused by us tightening the bolt using the wrenches. And so the first thing I did here was just draw a momentum and impulse diagram to help me visualize it, and then I was able to pull the equations we needed from that. And so here we have the momentum before, and we know that it is 0 because the tire is at rest. It's not spinning when you start using the wrench. And then we add to that our system's impulse, which is just this external force here of the moment created by the wrench. And that has to equal our system's momenta after, which is I omega. And this is the omega that we're trying to find here. And so taking this diagram and turning it into our equation, we have 0 plus our impulse, which is the sum of our moments times time. And in this case, we only have the one moment, and so it's just that moment multiplied by the time given in the problem equals I omega. And so to find our moment, we can use the perpendicular force multiplied by the distance, and the force and the distance are given to us here. And so we multiply 100 times the 0.46, converting the millimeters into meters, gives us a moment of 46 Newton meters. And then our time given in the problem was 10 seconds. And so we can plug both of those terms in to find our impulse. And then for our I omega term here, we are told in the problem that the wheel has a mass of 19 kilograms and a radius of gyration of 250 millimeters. And so knowing the equation for our inertia, given the radius of gyration is this, we can plug in our radius of gyration here converted to meters, so 0.25, and our mass of 19 kilograms, and that gives us an I value of 1.1875. And so we can plug that in for I, and then in this equation here we only have the one unknown of omega. And so solving for omega, we can find that the resulting angular velocity of this wheel comes to 3.87 radians per second. So that's the answer for this one. Okay, so this is problem number 5, and in this problem here we're not actually given any values to plug in to solve the problem. Instead, it's asking us to find a certain equation in terms of the variables that it's asking for. And so in this problem here we have this sphere, and we're told it starts with an initial value of omega naught and v naught, and we're told that the final velocity of the sphere is going to be 0. And the first thing it asks us to find is the required magnitude of omega naught in terms of v naught and our radius r. And so in order to solve that, the first thing that I did was draw another momentum and impulse diagram here. And so this is very similar to the given picture, except we know that our rotational force will be I omega, and this will be mv naught. And then that is added to our impulse term here. And so looking at all of the external forces that are acting on our body here, we have the weight pulling it down, mg. We have the friction force, F, and then we have our normal force. And all of those are multiplied by T because this is an impulse. And then that has to equal our momenta for the body, and all of those terms need to be 0. And so using that, we can write an equation for this. And so for this problem, we know that our system momenta has a rotational term and a translational term. And we can take the translational term and break it up into x and y components to give us 3 different equations. And so the first thing I did was the rotational term. So taking the moment at the center here, g, because that cancels out the most forces here, that cancels out both of these and just leaves our friction force, F. And so for a sphere, we know that our I value will be 2/5 mr squared, and that's multiplied by our omega naught. And then we add to that our impulse term, which is, like I said, just the force here multiplied by time multiplied by the radius. So we have those three multiplied together, and then that has to equal 0. And it's negative because I specified this direction as positive, and using the right-hand rule, it goes opposite of that in the negative direction. And so using this, we can solve this equation for omega naught, which is what part A is asking for, which gives us this equation here. But the question wanted us to find this in terms of V naught and R, and we still have time and force in this equation here, so we're going to need to find another equation to substitute into that. And so writing our equations for the x and y components in the y direction, we only have our impulse term, so we have the weight going down multiplied by time, and that has to equal our normal force going up. And so we know that our normal force equals mg. In the x direction, we have mass times our initial velocity v naught, subtracted from our friction force times time, and that equals 0. And so canceling out what we can there, we find that Ft equals m times our initial velocity v naught. And so looking at this term here, we can take this and plug it in up here for Ft to remove this term and get the equation in terms of what the question was asking us for, V naught and R. And so plugging that equation in, we can cancel the mass and one of the radius terms cancel, which gives us our answer for part A. So omega naught is equal to our initial velocity divided by 2/5 times the radius. And then for part B, the question wants us to find the time required for the sphere to come to rest in terms of V naught and our coefficient of kinetic friction, mu k. And so for that part, what we can do is solve this equation here for time, which gives us mv naught over f. And then looking at that equation, we can figure out what f is to get it in terms of our coefficient of kinetic friction. And so in order to find our coefficient of kinetic friction, we know that force equals mu k times n, and looking at our y components here, we know that n is equal to mg, and so we know that force is equal to our weight mg times our coefficient of kinetic friction. And so replacing that for f here, the masses cancel, and we get that t is our initial velocity v naught divided by our coefficient of kinetic friction mu k multiplied by g. And so that is the answer for part B for problem 5. Okay, so this is the diagram for problem number 6. Looking at this diagram, it looks like we have a wooden table here that's able to rotate around its stand. And then there's also a semicircular panel here that is attached to the tabletop using hinges. And we're told that as this table is rotating, this semicircular panel will be hinged down into the horizontal position. And the problem wants us to determine the angular velocity of the assembly after the panel has been released and come to rest against the plate. And so comparing our initial omega to what our final omega will be once this folds down. And so looking at this problem, we can tell that there are no external forces acting on this, and that all of the internal forces will have a net value of 0. And so there's no impulse for this problem, which tells us that we can use conservation of angular momentum in order to solve for our final omega in terms of omega naught. And so to solve this problem, the first thing that I did was just look at the problem and realize that these two pieces of wood, the tabletop here and the semicircular panel, are made out of the same material, and so the tabletop will have twice the weight of this piece with the hinges on it. And so that's what I've written down here. And then, like I stated before, we know that we can use conservation of angular momentum where h1 has to equal h2. And so by finding what h1 and h2 is, we can set those terms equal and then hopefully solve for omega final, our final angular velocity. And so in order to do that, we know that we need an I omega term for each of these. And so to solve for the I terms here, the impulse, or not the impulse, the inertia terms for the plate is just this circle here. So we know that that has to equal 1/2 mr squared. And that is the same before and after. And then the impulse is going to change when this, the inertia is going to change when this table folds down. The inertia for that semicircular panel will change. It's similar to when an ice skater pulls their arms in or out, how that changes how fast they spin. So that's the similar concept here for this problem. And so when the panel's in the vertical position, we can use our equation to find out that it should be, the equations from the book tell us it should be 1/4 times mr squared, and we know that that's 1/2 of the mass of the plate. And then we can do a similar calculation here for the horizontal panel. And so putting those terms together here gives us our I term for h1 and then h2, and then both of those have to be multiplied by our angular velocity omega naught and omega final. And then since these are like terms, we can just add those together, which gives us our terms for h1 and h2. And then from there we can, like I said earlier, set those equal because we know this relationship is true, that angular momentum must be conserved. And then that's what this equation is here. Looking at this, the mass and radius terms cancel on both sides of our equation, and solving for omega final, we can find out that our final angular velocity is 5/6 of omega naught, whatever that term is. And so that is the answer we were looking for problem number 6. Okay, so this is problem number 7 for this homework assignment. And in this problem, we're starting to look at a problem where there's an impact. And so in this instance here, we have this bullet that's traveling, and it's going to stick into this round block of wood, this wooden disc. And it tells us the height that this impact is going to occur at. And the first thing that the problem wants us to determine is the linear velocity and the angular velocity of this disc after the bullet has impacted it. So the bullet is going to stick in this disc, and we want to know the angular and linear velocity of this round wooden disc. And so to solve this problem, I treated it like a system. Just looked at the bullet and the wooden disc as one body. And so this is the first momentum and impulse diagram that I drew. And so we can see here that this is before impact. We have the bullet traveling in, and this is not moving or rotating. And then during impact, this is what the diagram will look like, and the bullet is wedged inside of the block of wood. And then after, the system will have an angular and linear velocity over here. And so to solve this problem, I decided to break it up into components. So I have the x and y directions, and then taking a moment would allow me to solve for what the question wanted us to find. And so looking at this problem in the y direction, the only forces we have are our weight and our normal force. And so the times cancel out, and we know that our weight is equal to our normal force, or mg equals our normal force. which we'll have to use when we look in the x direction. And then in the x direction, we have the mass of the bullet, which I labeled mb, lowercase m, b, times our initial velocity of the bullet, v naught. And then we have to subtract from that, because it's in the opposite direction, the force of friction here. And then that has to equal capital M, which is the mass of the wooden disc plus the bullet, times the final velocity of the wooden disc plus the bullet. And so looking at this problem, we know that this impact is really fast, it's instantaneous, and so we can assume that that time is 0. And so this friction force here in our equation we can cancel out and assume is 0, which leaves us this equation here that I've starred. And so rearranging that, we have an equation here for the final velocity of this system right after impact in terms of the mass of the bullet, the combined mass, and the initial velocity of the bullet. For our momentum equation, we take a moment of this system and it gives us this equation here. For our I term for the wooden disc, we know that that has to equal 1/2 mr squared. And so we can plug that term in, and we were also told that this height here is 1/2 of the wooden disc's radius, and so we can plug that in. And then we can solve this equation for omega 1 here, which is the angular velocity right after the impact of the bullet, which is this equation right here once it's all rearranged and simplified. And so that's the answer that part A wanted us to find, was the linear velocity and the angular velocity right after impact. For part B, the question states that we want to find and describe the motion of the disc and the diameter and determine its linear velocity after the motion has become uniform. And so after a little ways after this impact, the motion of this disc will become uniform, and we want to know what the linear velocity of this disc is at that time. And so in order to solve this, I drew another impulse and momentum diagram here. It's very similar to the one before. And then like a similar process from up above, we can use this diagram here we've created to write out our equation. And then this I term is the same one from up above. It's our inertia for the wooden disc, and so we can plug that in, and then we can simplify this to find out what our omega 2 is. And omega 2 is the angular velocity after the motion has become uniform, and v naught is our velocity after the motion has become uniform. And so looking at that and rearranging those, we come up with these two equations here for omega 2 and v2. And so these are the equations for the linear and angular velocity once the motion of this disc and bullet system becomes uniform. And so that is the solution for question 7. Okay, so this is the 8th problem for the Chapter 17 homework assignment, which is the last homework problem for this set. In this problem, we have another problem that deals with momentum and impulse. And so we basically have this balance beam here that's on this pivot at D, and this gymnast here jumps from a height h and is going to launch gymnast A into the air. And the question wants us to find the height at which this gymnast A will rise to. And we're told the height h of this gymnast when he jumps. We're also told the mass of both gymnasts here and the mass of this plank. And so in order to solve this problem, like in the previous problems, the first thing I did was draw an impulse and momentum diagram. And so here is before the impact. We have gymnast B falling down from height h, and then during impact they both are on the board, and then after gymnast B will continue down and gymnast A will begin to go upward. And so in order to solve this problem, the first thing I decided to do was take a moment about this middle pivot point here, D, because that would cancel out any of the forces that act at point D, like the normal force here. And then from there we'll be able to solve for what the question was asking. And so to take a moment at D here, on the left-hand side of the equation here, we have the mass of B and E going down and the velocity of the first gymnast B. And that adds to 0. The forces here and the impulse all cancel out, so there's nothing there we need to worry about. And then that has to equal this right side of our diagram here. And so we have the I omega term for the rotation of this plank. And then we also have a moment caused by each of the gymnasts. And so this is the moment here from gymnast A, and this is the moment here from gymnast B at points C and E. And so we have the mass times the velocity times the length L from the pivot point out to the gymnast, which is the same on each side. L is the same distance there. And so that gives us the right-hand side of our equation here. And then from there, what I decided to do was use our kinematic equations, where we know that velocity is r omega, or in this problem it's L is our radius. And so we can use that anywhere we have a velocity term to replace velocity with L omega. And so I plugged that in to our equation here to replace the velocities, and then I was able to factor out an omega term and an L squared term because there was an L squared in each term as well. And I was only able to do that after we plugged in our I value for this plank, which is 1/3 ml squared. And that m is the mass of the plank. And so factoring out that omega and L squared gives us this term here. And what we want to do here is solve for omega. And so solving for omega gives us this term here. One of the L's will cancel, and we're left with just one L on the denominator. But if we remember this kinematic equation here that we used before, we can replace L omega with VC. So we move L back over to the other side, giving us our L omega term. And then that can be replaced with VC, the velocity of this gymnast here that we're trying to solve for. To find the height, we need to find out the velocity. And so replacing that with VC, we have an equation here for that we can plug everything in and solve for that. And then we know this equation here holds true from our previous chapters on kinematics. And so if we can plug in our given values and find VC, we should be able to find the height of the gymnast. And so in order to find VC, we have everything here we need to except for this velocity term of gymnast B. And so we can use this equation here to find the velocity of gymnast B. And so then we can just plug in everything we were given. We were given the height, we know gravity. And so the velocity of point E here is 7.0036 meters per second. And then we can plug that in here. And now we have all of these masses. So we have the mass of C, the mass of gymnast E, and then the mass of the plank, which was all given to us. And so we can plug in all of those values and solve for our L omega term, which is our velocity of C term, and that comes to 3.7712 meters per second. And then we can plug that into this relationship and we can finally solve for h, the height which gymnast A will rise to. And so the final answer there, I'm plugging in the V of C that we just calculated and our gravity constant. We can find that the height which gymnast A will rise to is 725 millimeters. And so that's the answer for this problem. Okay, thanks for watching.